For decades, the standard red LED operated at a fraction of a watt. These simple indicator lights generate minimal heat, dissipating easily into the surrounding air. But industrial solid-state lighting and modern optoelectronics operate at entirely different power densities. To produce high-lumen illumination or encode data for optical communication, engineers must drive hundreds of milliamps of current through a microscopic active region. Only 30% of electrical energy in high-power solid-state devices becomes useful light. The remaining 70% is lost as heat. This massive waste energy concentrates entirely within a microscopic semiconductor footprint, creating a localized thermal hotspot of extreme intensity. To control the directionality of the emitted light, engineers heavily modify the geometry of the device's PN junction. Constraining the optical path shrinks the physical area available for heat dissipation, compounding the thermal load on the materials. A device designed to emit highly focused, efficient light generates enough concentrated thermal energy to melt its own internal structures if left unmanaged. In a standard PN junction, injected electrons and holes recombine in the active layer. This process releases energy in the form of photons, which scatter outward in a 360-degree sphere. This isotropic or surface-emitting pattern produces a broad, diffuse wash of light. It works well for indicator panels or general room illumination. Transmitting data through a single-mode optical fiber requires extreme precision. The fiber core accepts light only within a very narrow numerical aperture, a specific tight angle of entry. This graphic illustrates why diffuse surface emission fails for optical data transmission. The wide, unguided cone of light strikes the fiber at angles too steep for the core to accept, resulting in massive signal loss. To achieve high-bandwidth optical communication, the physical geometry of the diode must be engineered to suppress random surface emission and corral the photons into a targeted beam. The architectural solution is the Edge Emitting LED, or ELED. Its core is a heterojunction, a thin circular active layer of gallium arsenide, typically 100 to 150 micrometers long, sandwiched between thicker cladding layers of aluminum gallium arsenide. The gallium arsenide active layer possesses a higher refractive index than the surrounding aluminum gallium arsenide cladding. This difference creates a strict optical boundary between the materials. When photons are generated in the active layer, they strike this boundary. Because of the difference in refractive indices, they experience total internal reflection, bouncing continuously within the core without escaping through the top or bottom. The material sandwich acts as an optical waveguide. Surface emission is suppressed entirely, and the trapped photons are guided out through a single exit facet parallel to the junction. The result is a highly directional output, where the emitted beam radiance is defined by the equation B sub theta equals B sub 0 times cosine theta. This concentrates half the total optical power into a tight 30-degree plane. With a small beam divergence, this optical power can be launched directly into a single-mode optical fiber. This directional coupling drastically improves modulation bandwidth, enabling data rates of more than 20 megabits per second. By forcing all emitted light through a 150 micrometer active layer to solve the coupling problem, the architecture creates an extreme physical bottleneck. The exact structure that concentrates the photons also traps 70% of the injected power as waste heat in a microscopic space. Heat cannot easily dissipate upwards. The standard polyurethane paste resin used to encapsulate these devices is a poor thermal conductor, acting as an insulator over the active layer. This diagram translates the physical heat extraction path into an electrical circuit analogy known as a thermal resistance network. To keep the device operating, engineers must minimize the total thermal resistance from the internal junction to the outside ambient air. Nearly all generated heat is forced out through the backside of the chip. The first stage of resistance involves conducting thermal energy away from the active junction and down into the physical solder point. From the solder point, heat moves into the metal core printed circuit board, or MCPCB. Here, an aluminum or copper alloy base serves as a heat spreader, pulling the thermal load horizontally away from the diode. Finally, the energy transfers from the board to a finned heat sink, where it dissipates into the surrounding atmosphere through convection and thermal radiation. Passive heat sinks depend entirely on surface area and ambient airflow.
When device wattage scales up, conduction and natural air convection simply cannot move the thermal energy fast enough to prevent the internal junction temperatures from spiking. For peak power outputs, passive spreading is replaced by active cooling. Silicon-based thermoelectric devices are integrated directly beneath the substrate, utilizing a sandwich structure of N-type and P-type semiconductor units. By applying an external current, these units use the Peltier effect to actively force heat to flow from the hot junction side down to the cooler substrate, forcefully pumping thermal energy away from the diode. Whether utilizing passive spreading layers or active thermoelectric pumps, minimizing this total thermal resistance path is the strict physical bottleneck that determines if a high-power diode will operate continuously or degrade into failure. Fabricating these microscopic optical waveguides and their corresponding thermal extraction networks requires strict cleanroom environments and exact material tolerances. The architecture of the edge emitter evolved in the mid-1970s, directly adapting the physical structure of early injection laser diodes to create a highly directional, non-lasing light source. This graph demonstrates the strict consequences of thermal saturation. As the internal junction temperature rises, the physics of electron-hole recombination degrade. Luminous efficacy drops, and the lifetime of the device plummets. Extracting the 70% energy lost as heat dictates the ceiling on optoelectronic performance. If the thermal energy cannot be removed, you cannot increase the current to push more data. Pushing the boundaries of fiber optic communication and high-power illumination relies entirely on junction physics. Maintaining it is an exercise in advanced thermodynamic engineering.